That goes on for 3 minutes. Good Lord. So, shear. We're going to do a shear example, and then we'll be done with shear. There's some homework on it. I assigned due on Friday, so right before the break, because I know y'all are busy with other stuff next week. So let me know if you need an extension on that, like over the weekend or something. But I don't know if you'd rather it be done on Friday or be due on Monday of an actual break. So talked about if you watched the videos, how to find the shear that you need to design for, and then how to design for the shear. So finally, all that stuff we learned, shear moment diagrams, here's one place where it comes to make the banner. I have this simply supported beam. You can kind of think of it as like a little simply supported beam, 20 feet between the centers of those supports. So I need to find the reactions and draw the shear diagram. Straight into it. So what are my reactions for a 20-foot long simply supported beam?
I got 145.
Yeah. Right. Right, just 14.5 times 20 divided by 2, right? And if you remember anything, probably it's 0 at the center, positive 1, oops, oh, whatever. Positive 145 on one side, negative 145 on the other. See if I can draw a straight line. Yeah, pretty close. So we're gonna need this for a couple of things. First of all, we've learned that we can take our VU, what we need to design for, at a distance D from the face of the support, provided we meet these conditions. Loads are at the top, it's putting compression in the end regions, and there's no concentrated loads. So my beam is being loaded from the top. That means all of this is in compression, and there's no concentrated loads in that distance D. So I get to take, if I'm looking from the left side, I get to go 6 inches from the center of the support to the face of the support. 6 inches. And then I get to go another distance D, which is 27 inches. And this is where I get my shear design value.
Explain that one more time because you flat lost 6 inches in and then what?
Okay, 6 inches from the center of the support to the face. And then 27 inches, which is D, from the face to where your actual shear design is, because this distance which has
I
a,
just didn't see that D was given to me. I'm sorry. I
yeah,
thought you
it's up,
calculated
it's
that.
up at the top.
It's up at the top.
Yeah.
We're good.
This is coming out at a 45-degree angle. So everything from the face of the support at a 45-degree angle is in compression, and you don't have to design for the shear. So the critical section, I guess I should say that, that's the critical section. Is what they call it. Because that's the highest shear that you have to design for. The higher shear to the left of that is all in compression and does not really have a shear force in it. It'd be the same on the right side too. So really, if you're looking at your VU, it would be like, I'm gonna draw it again because I don't wanna, but you can make notes as you wish. Would really be say that. Terrible. With this distance being 6 inches plus 27 inches, so 33 inches. And this value, just use similar triangles, right? This distance right here is 10 feet minus 6 inches plus 27 inches. So my shear at the critical section is 145 kips times 10 feet, 12 inches per foot minus 6 inches plus 27 divided by 10 feet, 12 inches. Should give you about 105 kips, right? So instead of having to design for 145, then we have to design for 100. we drew our shear diagram. We get to take it a little bit from the face, 6 inches to get to the face, and then another 27D to get to our critical section, because we're allowed to do that because our beam is being loaded from the top. Similarly on the other side, like this is all in compression on the ends instead of shear. So we don't have to design until we get to that D away from the face. You can do that using similar triangles. Anybody have any questions about that? So how much nominal capacity do we need? Vn du over phi 105 kips. And if you don't remember, the phi for shear, all the phi factors are on page 391. Shear is 0.75. So we need a nominal capacity of 140. How much can I count on from my concrete? Because that will determine if I even need shear at all, shear reinforcement at all. BC is page 404. Look, I'm in the wrong one. If we assume that we're providing more than the minimum, we can use this equation. Lambda is for normal weight concrete equals 1. So we're gonna assume we have monoline concrete, if it didn't say it. We're assuming we have monoline concrete. That is one. And we don't have any axial load. That is zero. So my shear capacity from my concrete is 2 square root F times C EW. My beam width is 15 inches, and my depth is 27. I should give you like 51,000 pounds or 51.2. Pretty good, eat lunch. So I got 51.2 kips from my concrete, but I need 140 kips. So I need to make up for it with some steel. My nominal capacity is my contribution from my concrete plus my contribution from my reinforcement. So if I want to know how much I need from my reinforcement, just BN minus BC, 140 kips minus 51.2 kips. I need 88.8 kips of shear strength from my shear reinforcement. If you forget where that equation for my contribution from my shear reinforcement is, it's on page 410. the area of the steel and shear times the yield stress of the steel reinforcement, or your shear reinforcement, D over.
Now in the video, you talked about the equation below it. Can you explain again when we have to use which
That
one?
would be if you're on an incline. This assumes your shear reinforcement is vertical. This
Okay.
assumes your shear reinforcement is at some angle alpha.
Okay. So when we're designing for shear reinforcement, how do we know which one to use?
Is
this up to us?
Yeah, it's up to you, but I mean, use this one. Because
always, unless you just have to.
Unless you need to have some reason to go inclined. Because,
okay, cool.
Yeah, because shear is going to be, this might only provide shear the best in one direction, but you might have shear in two directions, like if you have a seismic load or something like that. You know, seismic or wind go both ways. So,
okay. So unless you have a good reason, just do.
Yeah, this is
the first
one you should use. Yeah. What am I doing? So from that equation, Vs is AV and if you solve for AV over S is what you want to know. This is 60 KSI steel, 27 inches. Should get 0.055 inches squared per inch. Really, it's inches, but it's inches squared per inch. You need to provide 0.055 square inches of shear reinforcement per inch of length. That's what that means. So I just said, okay, I need 0.055 inches squared per inch. That's AV over S. If I didn't write that before, let me just make sure. And let's say my beam section like that, and I have a hoop, or yeah. My area of steel in the cross section is 2 times that area of the stirrup bar, because I have one here and one here, even though it's all the same thing, but it's in different locations. So AB 2 times the area of the stirrup, because those two are both resisting shear. If I had a third bar in there, then it would be 3, and it was the same size or something, then it'd be 3 times. So if I use, let's say I use number 4 stirrups, number 3s and number 4s are the most common. My area of steel is 2 times the area of the number 4, which is 2. And my spacing that they would need to be spaced is 0.4 inches squared divided by that AB over S. It's something like 7.3 inches. So I could say, okay, I'm going to put number 4s, and you would need to round down to increase it, right? So you could put number 4s at 7 inches, number 4s at 6 inches, something like that. This is my maximum spacing for the strength requirements.
Would that be throughout the entire beam?
That is a very good question.
Like for the beams at work, we almost always have like the spacing at the ends are at 3 inches on center, and then you have some at 6. In the middle is usually like 10 or 12 inches on center.
That's where we're going after this. But yeah,
Okay.
that is the right question to ask. You can reduce how much you need because you don't need as much. Yeah.
So that this 7 inches would just be at the ends.
Right at the ends where you have the high.
Okay.
Yeah.
For that 33 inches, I guess.
Yeah. And this is where you as the designer get to make decisions. Like, you know, you don't want to over design it, like put one here at 7 and one here at 8.5 and one here at, you know, you have to create sections of spacing. But yeah, that's the next part after this. We do have some detailing requirements in chapter 9. We have maximum spacing and AV min. Our maximum spacing is on page 147. Okay, so we have to figure out if we need less than 4 or more than 4. F prime C, the square root F prime C DWD. And this is basically, right, this is 2 VC. VC was 2 square root F prime C. So now do we need more or less than double the VC? My required VS was 88.8 kips for square root F prime C BWD, which is 2. VC was like 51. So 102. So we need less than that. So we get to use that top equation. It's the lesser of D over 2, which is 27 inches divided by 2, 13, right? Or 24 inches. So our maximum spacing is 13.5. And we said 7.5 at the ends. So we're fine at the ends. That's all based on that little table 9.7.6.2.2. Right, and we're here because we don't need more than double the amount from the concrete. So it's the lesser of D over 2. That's along the length. We're not across the width, but along the length. Lesser of D over 2 or 24 inches. So D over 2 wins because it's 27 divided by 2 or 13.5. The other thing that we need to check, which we're probably fine, we're usually fine, but did we meet our minimum shear requirements? That was just a couple pages earlier. Page 136. That's not maybe then. We are a non-pre-stressed beam, so we need the greater of 0.75 F times C BWD of F by T or 50. So 4,000. That comes right out in PSI. So 15 inches, 60,000 PSI. We'll give you inches, but it's really inches squared per inch. So this should be 0.012. And this should be 50 is assumed to be a PSI. You want to write that in your book? You're more than welcome to write that. In case you don't remember. That should be 1.13. Doesn't matter because we're fine. At least at the edges. 0.013. And we are providing 0.055, right? So at least the ends meet AB min.
Should that AV have been 0.04 or 0.4? Or is that comparing to the AV of a jet?
Oh, yeah, I guess we could actually, you're right. If we say our AV is 0.4 inches squared, and we're providing it at, well, if we provided it at 7.3, then it would be exactly that, but I don't know, let's say we're providing it at 6 inches. At 6 inches on center, 2 times 0.4 divided by 6, 0.13.
What is that? 2 times 0.4.
Oh, I'm sorry, 2 times 0.2.
Okay.
It's like, that's really big. Okay. Right? Those are my 2 number 4s in a startup like that. That's why it's 2 times 0.2. Over.
Yeah, so we have to compare it based on what we're actually doing.
You're right, yeah. Yeah.
Okay, thank you.
So the next question, this is what Jonathan brought up, is do we need 0.055 inches squared per inch along the whole length? Because if I look at I'm going to look at half of my shear diagram. I only need that right at the critical section, and then right, my shear needs decrease as I go towards the center of my feet. So what I'm going to do, this is just an exercise. You can do it however you would like. I'm going to choose 4 different points. This is A, B, and at each of those points, I'm going to calculate how much shear I need. Compare that to my VC, my contribution from my concrete. If I need to make up for anything with steel reinforcement, or and then select. If it's not, also check AV min, because at some point you don't even need the minimum. And you can design AV over S along the leg. Where since your shear needs decrease, you're going to be able to space out your shear reinforcement more as you get towards the center. Open. 10 feet. This part is 33 inches. So 10 feet minus 33. I get 87 inches. And then just calculate those distances. This is just to give you an idea. You don't have to choose 4. You could choose more or less, depending on probably how long your beam is. Just to illustrate your needs, right?
Would there be a way to just relate that just to the spacing?
Yeah, there are. Yeah, there's other exercises, and I'm trying to remember if I've made you do it in homework or if I've done it in class. I need to look.
Because like the beams that we get, they almost always have the same kind of groupings. It's just adjusted along the length, I guess, depending on what is required.
How many different choices, like,
It's almost always like a group of 3, then 6 or 8, and then like 10 or 12.
like at the center?
Yeah, for the center to center spacing.
Yeah, one thing you could do, actually, maybe I feel like I did this. It's all coming back to me now. Yeah, another way to look at it is like, you draw your shear, like how much you need, and you draw, oh, that's not right, but, and then you plot what your VC is, which is like here, something like that. And so you know anytime that your shear is above your contribution from your concrete, you need VS to make up for it, right? That should say VO. And then if you look at half of that, anytime it's above half of it, which really the most important part is like here, you need AV min, and anytime it's below that, which would just be this length, no AV min. I don't know if that kind of makes sense, but the purple part, I'm going to take away this. Anytime you're above, your red line is your shear design that you have to design for. Your shear design force. If you don't have enough from your contribution of concrete, that's the blue line, you have to make up for it with shear reinforcement. So over this length, you need shear reinforcement for strength. Over this little length, anytime you don't need it for strength because your concrete has enough strength, but AV min requires you to have at least, if you need more than half of your concrete strength. Over this length, you need AV min. And then over right towards the center, you can space them out even further because you don't even need AV min. But you're probably going to put something there, you know, looks kind of weird. So that's one way to do it. I was just selecting a couple points upon along the length to kind of illustrate that. But yeah, you're gonna need it. Like, and maybe, I mean, I don't want to color on this anymore. Maybe you put them, like you said, at like 3 inches, maybe to somewhere around here. And then you can put 6 inches to somewhere around here. They don't have to necessarily line up with when you need AV min and when you don't, and when you need shear strength and when you don't. It's just where there's a natural boundary. You could also make a plot of the spacing. Like if you chose number 4s, what spacing do I need along the length? And maybe some natural breaks will pop out at you doing that. So that's a good exercise. I could amend your homework to do that. Yeah. So if I look at those points that I just said, like A, B, C, and D, if you calculate your VN or your V, yeah, calculate VN because it's easier. That's just, oh yeah, that needs to be VN because I didn't put any B's on my VC. So if this is 140 kips at point A, then just basically multiply that by a half or a quarter or 3/4. So let's say 140 kips, 70 kips. So my VC is not going to change. 2 square root of prime C W. This is just comparing how much shear I need at different points along the length to how much I can get from my concrete. So if I get 51.2 kips from my concrete, I need 88.8 from my tensile reinforcement. If I get 105, now 35 minus 51.2, I get a negative. So I don't need any from my shear. You can't get negative, right? All I'm doing is subtracting my contribution from my concrete to how much I need total. So column 1 minus column 2, except you can't get negative. So 35 minus 51.2 just means I don't need any steel for strength. So for at point A, do I need shear reinforcement? Yes, because I need it for strength. At point B, do I need shear reinforcement? Yes, because I need it for strength. At point C, do I need it? Yes, because I need it for strength. At point D, though, I don't need it for strength. But I need it because AV min shall be provided where VU is greater than that, which is essentially this equation is actually P times VC over 2, right? That lambda can go to 1 if we're in normal weight concrete. So VC is 2 square root F times C BWD. If I just divide it by 2. So wait, no. What? Oh my God, did I just delete everything I just wrote? That's super fun. I'll go back and rewrite it, but I'll start where we did. That's fun. So I don't need it for strength, but N is greater than BC, right? 51.2 divided by 2 is 26, 25.6. So I need AB min. And if my spacing, yes, maybe over S of S, maybe yes. If I assume number 4 stirrups, so my AB is 0.4 inches squared, 2 times 0.2. FY is 60, D is 27, and I input that VS that I have right there. This is my maximum spacing of 7.3 inches. Inches. This is based on strength requirements. Right? 34 inches, but this is based on strength requirements, and I just said earlier that, which I deleted, that my maximum spacing was D over 2, or 24 inches. Same here. So those are based off of the spacing requirements. So it just means I could maybe have a section where I have them spaced about 6 inches apart. And then the middle, I can space them out at 12 inches. And then 6 inches again if I can. So it kind of looks like you're looking at half the beam. I have some distance over which number 4 is 6 inches, and then number 4 is 12 inches. And this could be from the center point to that point B, maybe. So whatever that point B was. For about 55 inches. And then you could round stuff up maybe for 5 feet. That, and then this could be another 5 feet. About point B was about. So that's not actually looking nicely. What you'll ultimately end up with is from this, right from the center of the support to some point here, that was about point B. It ends up being about 55 inches, so I just rounded up to 5. Give you something like that. And then when your shop drawings come back, I mean, 6 inches and 5 feet is nice, but when it's like 8 inches or something awkward, they'll really say, okay, 5 divided by 6, and you where they're counting bars, and you decided, okay, did the detailer count the number of bars, and then they just shove them in there and about right, you know. We're not out there with a measuring tape making sure it's exactly 6.2 inches apart or something like that. We need 30 of them over here for over 5 feet and 10 of them over here over 5 feet, something like that. I'm not doing the math yet.
Yeah, and I think our guys have like a tolerance of plus or minus a bar diameter.
Yeah,
So
yeah.
it's gonna be off anyway.
Yeah. So really, it's 5 feet. So you'd be like, okay, I need 5 of them or 6 of them over this one length and 12 of them over the other length, or 13 because it's space. Because we're counting spaces, not bars. But that's why we do our shear moment diagrams. It's because we need to know the variation of the shear along the length so that we know how much strength we need from our, or strength we need and what we need to provide for our shear reinforcement. Because that 7.3 inches that we did at the beginning, that was just right where we have our highest shear. We can space them out further because we don't need as much. Does anybody have any questions about that? There it is. You guys wanna, you can do the breakout thing and look at the example to get with some, if you're ready. Just the shear reinforcement, not the. People.
as your VU. Hey, do you not have to compare like triangles because it's on a pin and a roller? So you just take the max shear as your VU?
As your maximum VU.
Yeah, okay. Just making sure.
So the reaction force is the maximum, is the VU? Is the
Yeah, in
maximum?
this case,
Oh.
because
Oh,
there's no dimension, right? There's no footing.
assume
This is
that
on a pin
there
and
is.
roller?
Take it DN. Take it DM.
DN.
Take it.
Oh, okay. Just use the 23 because
Yeah.
there's no footing.
Reduce it by that distance D. Yeah.
All right. That's what I was confused on because I was like, there's no dimension, so I thought maybe we didn't.
Yeah, do that. This is just a
Okay.
picture. Yeah. Let me go see if the other guys are doing
That
it.
changes things.
You guys doing it?
I'm checking the AV min right now.
Okay. Did you guys take you go to the critical section? Or no? Are you designing for the 60 or like the 50? What's the value? You know what I'm asking? Did you reduce your VU that you have to design for?
I just used 23.5. Like I didn't add anything to that for my
What
critical section.
yeah. So like the shear that you're designing for is like 53.7 or something like that.
Yeah.
Okay. Okay. The other group had a question, so
Because you didn't put it on there, I was just assumed like you didn't care about that. So
yeah. Yeah, just you can still, I mean, it's just a simplified picture, so yeah. Okay. I was just curious. Okay. You guys are the good ones, so you're probably fine. Okay. Let me know if you have any other questions.
all right.
tensile strength of your tension. So, but yeah. So 41.3 divided by 60 KSI times 23.5 inches. Should give you inches squared per inch, I think. Yeah.
Where is FYT given?
It's just, you just got to know it.
Well, wait, doesn't it say F? Why?
Oh, hey, how are you?
Okay, it's F. I guess I should have put a T there, but it's 40
40?
up at the very beginning.
Okay. Well, if FYT is 40 KSI, why would we want to be in pounds for VS?
You're not, you're in kips.
Oh, duh. I'm tired.
What'd you guys get for your maximum V?
For VN,
Yeah.
we got 77 kips for VN. VU, we got 57.8. You divide by 0.75. Is that incorrect?
What'd you get for your reactions?
61.8. We factored the loads.
Did you divide? Yeah, I have to divide by. Oh, what? Hold on. No.
Wait, what did you get for feet for a factor load?
Like 4.12, the 61.8. I just don't get the 50, the thing.
You told us to take it in by the
23.
measurement of D, right?
Yeah, 23 and a half.
Yeah. So
What?
61.8
The
multiplied
57.
by 30 feet converted to inches minus 23.5 over
15
30
feet.
feet.
15 feet.
Oh, you do half of it?
Well, because think about your shear diagram.
Yeah, that's right. I just missed it. So it'll be up like half of what we just said. Son of a biscuit.
I'm just redoing all the notes from that I erased.
That you erased?
Yeah. Like a dumbass. Okay.
Oh, should we get 53.7
Yeah.
and then divided by 0.75?
26.87 for VU.
We should get a
No, I got
53.7, right?
53.7, and then for VN you get 71.6.
53.7.
Yeah, 61.8 times 15 times 12 minus 23 and a half over 15 times 12. Right.
Oh.
what I wrote here.
So VS should be
Yeah, I
36,
got to, you
35.9.
said 53.7.
Yeah. If you guys want to, you know, we got about 9 minutes left. If you want to quit, I can write. So, I figured we only had a few minutes left, so I know y'all are tired. So. There's everybody. Most everybody. I don't know. Josue and Jasmine like peaced out. So so I get reactions of right 61.8 kips. My VU at the critical section.
Can you share your screen?
No.
No? Oh,
Yes. Thank you. uh, 53.7. I need, at that critical section, I have my VC, and I need 35.9. So just barely need anything. No, I don't. I'm lying. I need something, but let's see. I got like an AVFS of, and that could be number 3s at like 5 inches, or number 4s at 10 inches. And then you can just go on from there, designing it. But you guys are going to do that in homework anyway. So just wanted to practice those numbers. Did you guys get similar ones? Like Jonathan and Garrett and all that?
say what?
Did you guys get similar numbers?
Yeah, we got 10 at the ends and then the max spacing of 11.75 pretty much in the middle, yeah.
Yeah, not a lot needed because that maximum spacing is going to limit you, right?
Yeah.
So there's not a lot of difference between the ends and the middle because your max spacing.
Yeah,
It's like an inch and a half difference.
Yeah, it was like, I got like 11.75 inches or something like that. So you could put a bunch of number 3s and then spread out number 3s, or just number 4s at like 10 inches along the entire length.
Yeah.
Is kind of what that means. So anyway, you guys have homework on this. You can ask me questions if you want, but then we're finally gonna move on to columns and finish out. We have 2.5 weeks left of class to cram columns in there. So yeah. It'll be fun, but I'll let you guys go enjoy your weekend. So thanks for sticking around.
I've got senior design questions as always.
Okay.
You might want to say that too.
I've got a question too about FE stuff.
Okay.
Go ahead, Justin.
Garrett's
You go
like,
first.
yeah.
Well, you done passed, Justin. What do you have questions about?
Do we need to send the university anything like for our FE?
Did you get your score?
Yeah, they just said pass.
There's like the balloons coming down.
Hold on, I can throw Dr. Pepper cans down.
Like, you passed on the first try, Justin.
Yeah, no, I'm pretty excited. So
yeah. Forward me the email. That's all you have to do.
okay, sweet, sounds good. I can do that.
Yeah. Yay! I got one of you. I don't know if anybody else is taking it.
I haven't heard of anybody else taking it yet. Well, I don't know. I know Caleb and all them got a bunch of free study guide stuff now. So,
Yeah.
because if you name it, I had it, and I didn't use any of it. So,
How do you get the free study guide stuff?
well, it wasn't free for me.
There is oh yeah, because I haven't looked. Justin, you signed up for that thing, right?
I did, and I never used it.
Oh goodness, okay.
The
Yeah.
one that you set up, Dr.
So-
Turner?
Yeah, the one that like I know 2 people signed up. I haven't looked in like a month though. So.
What was that, like $99 or something?
Yeah, it was like $99.
That's probably what I'll do.
That's supposed to be a super good way to do it. It's what I've heard, but I just never used it. So,
Okay.
because my internet at the house is garbage.
Yeah.
It's a step above Caleb's.
Which is not existent.
That's exactly.
Right.
Yeah, his you gotta send the packets via pigeon,
It's not that bad.
like a
Pretty
pigeon
close.
carries punch cards.
Cool.
I felt really bad about being such a space cadet yesterday. I had the worst headache.
No, it's okay. It's okay. It's probably easier for them to look at the stuff and give feedback anyway.
Oh, but still.
Okay. Okay.
Okay, I'm gonna get out of here.
Yeah, you guys have senior design questions. Go for it.
Yeah. So we've been working. Me and Jonathan are a team, even if we're not a team, if that makes any sense. So we do everything together. Interior design columns.
Yep.
For the footing, you do like a single footing for the interior column. But for the exterior columns, do you have to do a continuous footing along the whole wall? Or can you still just design for a footing for the one column?
Design the footing for the one column. Yeah.
Yes, that makes it a lot easier. Okay.
Okay,
I
well,
thought
That's what I thought.
was supported by that continuous footing.
The wall, they might say differently, but it could be that you have like a footing and then a continuous between them, but it'll be narrower because it's only supporting the wall, not
okay.
the building columns.
Is that
What
how
I
I
was
would do it?
telling,
Go ahead. Go ahead. Sorry.
isn't the slab on grade supporting the wall? Because we added the wall weight into our calculations for the beam. Because I asked him about it. I sent an email and he told us to add the wall weight into our deliverable 3 calculations. So the beams
I
and
don't ever
girders
see
are
any
supporting the
emails.
slab on grade.
Okay.
So isn't the slab on grade supporting the wall? So you wouldn't design for it twice, right?
Right,
Like you
well, I
wouldn't
mean,
have to, I don't know.
The beams are going, I mean, the beams are supported by the columns, right?
Yeah.
So it's being
So
designed.
the footing still ends up in the columns.
Yeah, so there could be still continuous footings between them, but
Well-
design, you know what, this could be a good question to ask, but just like,
Yeah, but they don't give us a response forever, and it's always confusing.
okay.
It
Well-
really is.
So for our project, we're in Minnesota and we have to do a deep continuous footing. And you're saying that we would go ahead and put spread footings for the columns, like we would do that. I'm not explaining it very well. Like do the
When I'm gonna look something up.
I'm just imagining in my head like a continuous footing, but the columns
The columns
just
are
being
like,
wider right there.
yeah. Let's see. Typical columns, okay, and then I feel like Paul put some stuff up there.
Yeah, I try to look at their stuff because it does help.
Yeah.
I mean, there's no question for the interior column, and like I think our calculations are right on that. But
Hey, Dr. Turner, before I hop off here,
Yeah.
I just sent you an email.
Okay.
I couldn't like send the actual email to you because I have to log into my NCES account.
Mm-hmm.
So I just took a snip of like my results page.
Okay, that's fine.
I take it that'll work, right?
Yeah, that should work.
Okay, perfect. All right, then. Well, I'm out. I'll see you.
All right. Let me go back and see what people did last year. That's sometimes what I do.
You should send us some of that stuff.
I already did, you guys. I didn't say it was good though. You guys used it.
No, the ones from JT and I guess Brittany, that was pretty good.
Yeah, yeah. I was like, these are what it should look like.
Like she had the inside scoop anyway. She works over
Right.
there at Cromwell.
Yeah, design a foundation for each footing.
okay,
For what? For each?
Yeah, design a footing for each column is what I'm trying to say.
And then
so
will
Jenny, when you
that
start doing it, when you
Okay.
design your footing for your interior column, do the same for your exterior columns. That's what she's saying.
No, I'm saying for each column, design a footing, and they might not be the same.
Yeah, so you could maybe have 3 different ones.
Yeah, but your calculations is the same, is what I'm saying. You know,
Your-
Yeah, the way you get it would be.
the way you do it's the same, but you're gonna
Your
get
method.
different results. Yeah.
So
So
if you
is-
were designing for a continuous footing, like in that simplified footing design, it has the area footing is equal to your PU over 1.6 times your soil pressure. So if you're doing it for a continuous footing, would you just like times that by 1 foot or something? Like how would you get the width of your footing that is required?
Well, you don't need to design
It might be a completely different.
Yeah, you don't need to design the continuous footing. We're just designing the square footing for the column.
Okay. And I think, I don't remember which of the footings that it was, but they, on that first deliverable, they commented on one of my footings that I had on my schematic. They're like, that's way too big. Like, I didn't even mention it, but okay.
Yeah. Well, if you have really bad bearing pressure, then allowable bearing pressure, then you're gonna have, and I guess they also talked about, I think, did they say footings were designed for service loads? Is that right? Not factored?
Yeah, you don't have to factor them.
Yeah, not factored in.
Yeah, that's right. Okay. Sorry.
Well, I ended up having to design a footing because they wanted me to break out my excavation, my footing excavation from everything else because it was 4 feet deep to get below down to the frost line.
Oh yeah. Yeah, because you guys are down in or up in Minnesota.
Yeah.
Yeah. I think last year JT and Brittany's team, they were in Alaska and they had terrible bearing pressure. They had like 16 feet like footings.
Oh wow.
Which is not what you're gonna do. You'd switch to like piles or something.
Yeah.
But this is just more of an exercise, you know, to familiarize yourself with footings and stuff.
Process and stuff.
Yeah. So.
Yeah, on that first deliverable, they marked it for me to decrease it down to like a 2 foot wide shallow spread footing around the perimeter. So I don't know.
Yeah.
I think I ended up doing 3 feet wide on the footing because that was something that was pretty common when I was in estimating. So I was just like, okay, 1 foot wide foundation wall and 3 foot wide footing sounds good.
Yeah. Well, and now that you're actually designing it, you can go ahead and update your excavations and stuff if they need to be updated, you know.
Oh, I did do that already.
Okay. Okay. I was like, it's a continue, you know, it's a process here.
Yeah. I did already fix that. Okay, I'm gonna hop off. I have an appointment. Thank you.
Mm-hmm. You're welcome. You guys good for everything else or more
Yeah,
questions?
unless you have any other questions. That's the only thing that we were discussing for him. So
Yeah.
Okay. Have you guys looked at RAM yet? Okay. It's gonna be
I'm just pointing the finger at Cami. She's got a drafting degree. She's doing all that. I hope she does at least.
well, RAM is the structural, not
Well, no, that one, yeah, we're all completely green on. So
yeah. That's gonna be your Christmas break.
I figure I'll end up.
yeah, no, studying for the FE will be my Christmas break.
Yeah, no kidding. But
I'm taking it right before we come back.
Okay.
I figure I'll probably be mostly responsible for that whole next deliverable.
Yeah, I purposefully chose who was in charge of deliverable 5. I was like, Jonathan will want to do this. Want to.
Have to.
Yeah, more have to.
Probably be the best, most successful at this. Okay. Well,
All right. Thank you.
you guys have a good weekend, I guess. So.
All right. Bye. Thanks for the help.
You're welcome.
Yeah.
Bye.